Hello, everyone. Welcome to this week's GOCC. Today we have Nate Lesnovich talking about splines on Cayley graphs of the symmetric group. But before we get started, as always, we want to remind everyone of our community statement, which you can, of course, read in full on our website. And the three guiding principles of our community statement are: first, we are all learning; second, everyone has something to contribute; and finally, no one has all the answers. And so please feel free to ask questions at any time in the talk. You can either address them directly to the speaker, or you can put them in chat and one of the organizers will make sure Nate gets them. But without further ado, Nate, take it away.
All right, let's get this up. Also, thank you very much for having me. I'm excited to talk today about what I've been doing for the past couple of months. Splines for Cayley graphs on SN. All right, so I'm going to start out with like a bunch of standard, bunch of definitions, right? Just to kind of get the ball rolling. Some of them will, a lot of the first ones will be relatively standard, and they will get progressively less standard as I go on. So I'm going to take a graph G on a set of vertices V and edges E, right? Where E is some subset of, that's a very large pen, some subset of V cross V. I've written down two examples, right? The first one here, I'm going to use brackets for the set, bracket integer for the set 1 through that integer. And I'm going to draw my graphs with dots and lines, dots for the vertices, or circles for the vertices, lines for the edges between them. So the edge 3, 1, 2, 2, 3. I have those two edges. I will call this the path. And you can imagine larger paths simply by extending out the line. And I have here a graph on 4 vertices, 1 through 4. I'll call this one the claw, or the 4 claw. And you can imagine larger claws or stars just by, continually adding edges off of that central node. So the graphs that I'll be talking about today are simple and undirected. So we're not going to see any loops, no edges back to oneself. We're not going to see, our edge set is not going to be a multi-set. The edge ij is the same thing as the edge ji. So we're also going to be undirected. So simple graphs, one thing we will be seeing is edge labels. So that's just going to be some function script L from the set of edges to the polynomial ring, which I will sometimes write as this. So my little sub bullet notation is going to be T1 through Tn, or 1 through n. And the idea of the construction is we're going to take a graph gamma on the integers 1 through n. And I'll always notate that as gamma. And we're going to construct from it a graph, a Cayley graph, script G sub gamma on the symmetric group. The idea is that we're going to conflate edges E, say from I to J, with the transposition in Sn ij, that switches I and J. And we're going to construct that graph. I'm going to do it by example first, by right multiplication. So the edges between, W and V, or I guess I should probably write W and Wij, and I shouldn't give it a direction because I said they were undirected. If Ij is in E. So I have written here S3. I'll write for you the path example. So we're allowed to write multiply by 1, 2, i.e. switching the first two elements in the permutation we see. And we're allowed to write multiply by 2, 3, i.e. switching the right two elements in our permutation. So switching the first two, switches 1 and 2 here, switches 1 and 3 here, and switches 2 and 3 there. So those are all of our 1, 2 edges, and then switching 2, 3, the indices, the elements in the indices 2, 3 give us those last 3 edges. And some of you might recognize this as the, I say, right, weak Bruja graph. And that's always, whenever you have the path, that's what this is, right? It's going to be the right Bruja graph. And it'll, you can give it a natural order as well, just taking this graph I've seen as I've drawn it as the Hasse diagram for the poset. So, right, I've drawn like a little table out, right? We're gonna have our gamma vertices 1 through n, edges, all right, I less than j normally, just to make sure I don't repeat myself there. And then for G sub gamma, our vertices script v are going to be permutations. Our script e edges are going to be this set, which is the same as right multiplication. And our labels, which is the only part of this construction I have yet to tell you, what we're going to do is if for an edge WV, we're going to assign to it the polynomials t sub w, the polynomial t sub wi minus t sub wj. If that is our edge. Alternatively, right, what's the best way to say this? The transposition that is WV inverse in this case, right, would be ST, then we'd write TS minus, or maybe I shouldn't use T, SR, S comma R, TS minus TR. So to each right multiplication, right, we're switching indices, but there's the corresponding left multiplication by a transposition, which is switching the two numbers that you see in those indices. And that's how we're going to construct these polynomials. So I'll do the labels up here, which I believe I do in green later, so I'll try to be color consistent. So for this lower right edge, we switch 3 and 2. Here we switch 2 and 1. Here we switch 3 and 1. 3 and 2. We switch 1 and 2. And finally, we switch over here on the right, T 3 and 1. So this here is the edge labeled Cayley graph for the path of length 3. I've printed out for you the claw, so it'll be on S4. And I think like the main purpose of this example is, I suppose, to convince you that the normal like Bruja order graph that we get no longer applies when we don't have the path. There's not a unique maximal element here. Everything is still, the graph is still regular, so every single vertex is going to have here 3 edges adjacent to it. because we are allowed to use 3 transpositions from gamma. Yeah, and I've done out all of the edge labels here. I did it in tech. All of the examples that I'll be doing going forward will be using the path, merely for the fact that this is too large for me to repeatedly draw and have it be readable without zooming in and waving my hands along.
I've got a quick question.
Yes.
So you mentioned that this is a unique maximal element, but these are graphs, and so, not cosets. But are we just saying distance from 1, 2, 3, 4?
Yeah, distance from identity does not give you a unique maximum.
Okay.
Yeah. The I would say the natural order imparted by right multiplication doesn't give you,
Sure.
that. Good catch. I used that was poor language on my part. Thank you. Cool. So these are the graphs that we're working with. This is the Cayley graph. To kind of complete the definition for the title of this talk, right? A spline on our labeled Cayley graph is an assignment row bar from, we're going to assign to each vertex a polynomial, such that, right, if WV is an edge in our Cayley graph, we want the difference along that edge to be contained within the ideal generated by the label for that edge. So this, right, we're studying the splines, and this particular definition, I suppose, removes the inconsistency that I let slip always in the beginning of the talk, because it doesn't matter later, that ij is equal to ji as a transposition. So this label function, as I have written, doesn't necessarily make sense, but I really care about the ideal, and -1 is a unit, so we're all set. Yeah, so differences along edges need to be divisible by the label or contained within the ideal. So the first and easiest example is if we set 0 everywhere, that is going to be vacuously contained within all of our ideals. So you can always construct a spline on a Cayley graph. In fact, if we just assign the exact same polynomial to every single vertex, then it's going to be the exact same situation. A little bit more unique of an example, which I will mention again all the way at the end of the talk when I talk about some other work and other things happening. If we choose an index I, or some element from 1 through n, and we decide to give W T sub W of that index, so I've chosen here 1, and if I give T of 1, T sub W of 1, so I put T1 here, T2 here, T2 here, T3 here, T3, and T1. That will also give us a spline. And I guess like the quick way of seeing it is along an edge. This switches, I'll use a different color. I will highlight this right here. Switches the second and third index, right? So it doesn't do anything to 1, so our polynomials are the same along that edge. So you see a T3 and a T3. If you do switch, if you do affect your index along that edge, then it is explicitly going to be the label that we give it. It's gonna, this one gives it T2 minus a T1. A running example that I will end up using quite a lot and also to demonstrate that they don't have to be supported everywhere or nowhere. We can have zeros all over the place. If we place T1 minus T2 at the identity and T1 minus T3 at the transposition 2,3, that also gives us a perfectly good spline. And to quick check, if you subtract them, you get, depending on which one you do first, T2 minus T3 or T3 minus T2. All right, so some quick facts to note. If rho bar and sigma bar are splines and F is some polynomial, then multiplication by a polynomial, where you do the natural, you just multiply by that polynomial at every index that you see, that is also going to be a spline. It's not going to change any of the divisibility criteria. And the addition of two splines also going to stay. And these are like, I guess the story of splines is also kind of related to the fact that this is a local condition. We only have to check every edge. So if you check an arbitrary edge, you're all set. And these are pretty easy to convince yourself of, at least via example. So what does this give, right? Given a gamma, right, we're going to construct a G gamma, or labeled Cayley graph, and we're going to consider all of the splines that we can construct on that labeled Cayley graph, and we're going to call that the module of splines from, this note. So it's the polynomial module M sub gamma, which is all of the splines. All right. And a little bit of a fact / exercise. Since the label function is homogeneous, the ideals that we're going to look at are homogeneous ideals. And again, kind of by a local condition argument, it's not too hard to see. M gamma is graded by degree. So if you have an F bar spline and you take the ith graded piece just by at every element of the symmetric group, I only want the monomials of degree I, then this is also a spline. Our graded piece is also a spline. So our first main overarching goal in this project is to understand this module. We want as much information on it as we can get. So for context, history, and also a little bit of motivation, this is understood when gamma is the incomparability graph of a 3 + 1 and 2 + 2 free poset. So that's a poset that doesn't contain either of these as a sub-poset. So in that case, gamma can be associated with some geometry. It can be associated with a Hessenberg variety, and in that case, M gamma is isomorphic to the equivariant cohomology of that Hessenberg variety. So this is this is getting into like the geometric background, and a lot of the initial motivation for this work is this module is well understood in those cases. You have generators, you have freeness, you have all of the normal things that you would want about a module. So what do we want? We want generators, and we want to know if this is ever free. Preferably, we would like the generators to be minimal, if we can. Freeness is not guaranteed. Just, I suppose, for a computational example, the claw that I showed earlier, the module of splines on the claw is not a free module. You have some higher order relations in a minimal generating set. What we can do, as it's not right to call it a workaround, but right, if we take the splines T sub I to be, just put T sub I everywhere, right? So T sub 1 would be every element of the symmetric group gets sent to T1. And we quotient our module of splines by the ideal generated by them, right? What this is essentially doing is removing the ability to multiply by polynomials, and what we get out of it is a C vector space. And here we have the questions that we actually, here there's quite a bit more structure, and we can ask about dimension. So we want generators, we want to know whether it's free. We know if we take our quotient, we're getting out this vector space, and we'd like to know its dimension. I have two results to share with you in this direction. So first, and this is more of a commutative algebra fact, all minimal homogeneous bases of M gamma have the same size, which is very good news for the dimension question, because this M gamma is graded. This is a homogeneous mod, so we really get a graded C vector space, and oh, good news for us, if we have a minimal homogeneous basis, I shouldn't say basis, I should say generating set. It'll project down to a basis, right? So all of those. So we're searching for minimal homogeneous generating sets. And second, the first graded piece, or perhaps maybe the sublinear piece of our module M gamma, which I'll write with a superscript less than or equal to 1 or superscript 1. If you take only the submodule generated by linear splines, that module is free. So a lot of the questions that I'm going to talk about in the second half of this, I'm going to be able to answer it specifically for the linear case, because we have freeness and there's no higher order relations to mess everything up. So we have M gamma. We want to study this model, this module. I have kind of one more piece of the construction, and that is the dot action. So definition, the dot action is a graded symmetric group action on this module given by this formula, which, I suppose in words, what we're going to do, W is going to act on a spline, and it's going to move the polynomials you see by left multiplication. That's this piece. And it's going to shuffle the indices of the permutation of the polynomial that you see there, also by W. So we can do that in either order, it doesn't matter. We move them by left multiplication, and then we shuffle around those indices. So, to show you how this works, right? If we're going to dot action the transposition 1, 2 with the spline that I used as an example earlier, what are we going to do? We're going to move by left multiplication. So let's figure that out first. So we're going to switch 1 and 2, the numbers 1 and 2 that we see. So switching 1 and 2 sends the identity here, and it sends 1, 3, 2 to 2, 3, 1. Right? So we know where those two pieces are going and what's going to happen to their indices. Everywhere we see a 1, we're going to write a 2, and vice versa. So our new spline is T2 minus, oh, not there, I guess that wasn't, though I had yet written something wrong. T2 minus T3 and T2 minus T1 is going to be our new spline after we apply that action. And everywhere else we're zeros, and that's not going to change anything. So that's how the dot action works, right? Our second overarching goal, I would say the one that I focus on more, I suppose, than the structure is I want to understand the dot action on this module. And in particular, the ideal that we mod out by before is SN equivariant under this action, which means that our dot action up top can be pulled down to a dot action on our quotient, and now we have an SN representation on a graded vector space, otherwise known as a graded representation. So this is getting into the representation theory side of things. So what I really want to do is understand the dot action after I take that quotient. And again, as history background / motivation, why should we be interested in this question? When gamma is in the incomparability graph or Hessenberg situation, whichever way you like to think about it, the dot action representation on the quotient under an involution corresponds to chromatic quasi-symmetric functions. So this is getting into Stanley-Stembridge conjecture questions, Sheresian-Walk's conjecture / Brosnan and Chow theorem questions, all of that stuff. We're taking a generalized look at it. We're taking different graphs. And kind of like where I'm moving with this in this situation, permutation representations, not to speak improperly, quotation whose point stabilizers are Young subgroups, but I'm going to just keep saying permutation representation. Permutation representations on the left are corresponding to E positivity on the right, which is all of the Stanley-Stembridge questions. So from now on, right, I'm going to tell you what I can about this representation, and I'm going to take gamma to always be a tree. In other words, the transpositions that I'm taking, I want them to be a minimal generating set of transpositions for the edges. There's going to be, on SN, there'll be n minus one of them. So, as a construction, right? Remember, gamma is now our tree on N with edges E. With any subset B of our edges, a coset spline on the coset, on the reflection subgroup generated by those transpositions is this F bar sub E upper B, defined by if we take it at some element V in Sn. If V is an element of our reflection subgroup, we're going to product over all of the edges in the complement and give those polynomials I have written. And if V isn't in our reflection subgroup, we're going to take the value 0. And a coset spline on the actual, coset of that reflection subgroup, WB, what are we going to do? We're just going to hit the identity, what I will call the identity coset spline With the dot action, that's going to move its support by left multiplication, like we saw before. So it's going to be that left coset. And we know, well, a little bit of an exercise, the identity coset spline is the spline. We hit it under the dot action. It's also going to be the spline. For an example, right, I'll walk through most of the coset splines for the path. So the identity spline, which I've written here as like blackboard 1 bar. I'll take, I suppose I'm assuming here that the empty product is 1. So B is equal to E, otherwise known as, right, so E minus B is empty. So we're going to end, our reflection subgroup is going to be all of Sn, and we're going to see 1 everywhere. On the complete opposite side, if we want B to be the empty set, which means our product, not that one, that one. Our product over this difference that we see above is going to be as large as it can be, and that's going to be this spline you see up here. So it's, I suppose I'm also taking the convention that this, right, the reflection subgroup generated by nothing is really the reflection subgroup generated by the identity. Cool. So that's one. Those are kind of like the 2 extremes, and in the middle, right? If we choose 1 or 2, 3 as our subset of edges, then the first, or one of the first examples that I showed you of a spline is our identity coset spline. We computed above its dot action, with 1, 2, and there's only 1 coset left, and it's the third one that I have written there. So those are all of the coset splines associated with the subset just 2, 3. And if we were to, there's 3 more. If we were to just take the transposition 1, 2, and they look very similar, they're just on the other 3 edges. All right, so proposition, our module is generated by coset splines. So if you take the set of all coset splines, we have a generating set. This is very, very not minimal. There are a ton of extra elements in that set, and one of kind of, I suppose, my active areas of research at the moment is trying to cut that down as much as I can in a reasonable way, so that I might be able to say something about minimum. What we can do, and this is getting back to the nice part where less than the first graded piece is free, we can write down bases for this one. So theorem, the following is a basis for the first graded piece. This is all of the linear coset splines. So we're subtracting off a single edge up here from our identity, from our edge set, which means our product is going to have 1 element in it. So it's going to be linear. So all the linear coset splines that aren't supported at the identity, together with the spline where I put 1 everywhere. That forms a basis of the free module M gamma upper 1. So I can also tell you what the dot action representation on this, but in order to describe it in a meaningful way, I have to define a few things. So, well, 1 or 2 things. So a permutation representation, again, for those familiar with the representation theory side of this, parentheses, on cosets, I'm being a little bit informal here, of Sn is, I'm going to call it the action of Sn on cosets of young subgroups. Young subgroups being, right, this would be perfectly good young subgroup. So as a subgroup of the symmetric group on 4, we're going to take the symmetric group on subsets of 4, so 1, 2, and 3, 4. I'm going to call H sub lambda for symmetric theory reasons. For symmetric function reasons, I'm going to call it H sub lambda. The action of Sn on cosets of the young subgroup S lambda, where lambda is in truth a partition, but some list of integers given, and that gives that product. So H21 should be the natural left multiplication action of S3 on cosets of S2 cross S1, where S2 cross S1 is really the identity and the transposition 1, 2 as it lives inside of S3, because that 1 fixes the third element. So that's a permutation representation, probably my favorite type of representation. I work with them quite a bit, right? So theorem, the dot action representation on our first graded piece, quotiented by the ideal. So it is the representation. I'm talking in the vector space context, is a sum of permutation representations. So in this case, what we have here is in the path case and in the first graded piece, what we want to be able to prove for the graded Stanley-Stembridge conjecture. Is another, I suppose, way of motivating this theorem. And it's much easier for me to show you what that representation is than it is to try and describe it in excruciating detail. So I have here written a tree, and what we're going to do is for each edge, right, that I'll label here, we're going to get a particular permutation representation. So for gamma, the representation on M1, M gamma 1 cross ideal that we had before is, so our first contribution is going to be special. It has to be leaf, an edge, a leaf edge, I suppose. That is going to give us something trivial. So this is on 1, 2, 3, 4, 5, 6, 7. So I should write an H7 there. And for all of the other edges, what we're going to do is we're going to cut and look at the sizes of our 2 component pieces. So if you remove an edge from a tree, you have the disjoint union of 2 trees, and we want the sizes, right? How many vertices are in each one of those components? So if we cut at B, we have a size 6 and a size 1. If we cut at C, we have a 4 and a 3. D gives us a 6, 1. E gives us a 5 and 2, right? 5 and 2, and then F will give us our last piece at 6, 1. So it is a permutation representation, and I can tell you from the tree exactly what it is. I also have a permutation basis from this. This proof is, the proof of this theorem is constructive. I construct a different basis from the one that you saw before that explicitly works like the action of Sn on cosets of Young subgroups. So, right, that's, I suppose, the end of the talk that I'm going to talk in any detail about. Some future directions / other results. Trees tend to perform relatively well. As you start adding edges, it becomes more difficult until you add enough. So if a graph is k-connected, which means you can delete k-1 vertices and you still have a connected graph, any k-1 vertices, then the dot action representation on the k-1th graded piece is trivial. You get however many copies of Hn or Sn as you have basis elements. That, if you're very, very familiar with the Stanley-Stembridge side of things, there is an LLT representation side of all of this, where I'm just going to quotient out by a different maximal ideal. Like maybe I call the first one the left ideal and the second one the right ideal. So the ideal where I put T sub W of I everywhere. Those are the generators I'm going to take for this right ideal. That's also Sn equivariant, so, and it's also maximal. So we get an Sn representation when we take the quotient. We can ask, what is that representation? I can answer that for trees, and I can give you, a basis of that vector space that shows that kind of, well, it's not H positive, but it also has to do with edge deletion, and answering that side of the story as well is something I look forward to trying in the future. And of course, linear representations for non-trees, especially knowing that that submodule is still free. So yeah, I'm happy to answer any questions. Thank you for having me. Thank you for listening.
Let's all thank the speaker. Okay. Does anyone have any questions? Okay, then I can start the question. So, way back near the beginning of the talk, you said that these things are well known if you are the incomparability graph of a 3-1 avoiding post set and a 3-1 and 2-2 avoiding post set, right?
Yeah.
Right. And when you mentioned Stanley-Stembridge, it's like, that believable that these things would be showing up. But I guess my first question is that, so if you are the incomparability graph of a 3-1 avoiding post set and a 2-2 avoiding post set, that means that you avoid, as a graph, you minimally need to avoid the claw and avoid 2-2 as induced subgraphs, because
yes. So that's, yeah. So the claw example is outside of that
right
correspondence. Yeah.
But there are more restrictions on just to be the incomparability graph of a post set. Like you need to be a perfect graph, like among other things.
Yeah.
And so I was wondering if just there's any researcher hoping to like, what if we're just claw free and 2-2 free? Like, ignore the incomparability graph of a post set. Because yeah, the claw looks like it's a problem. And there are lots of nice things about claw free graphs.
The claw is the claw is problematic. It's for computational purposes, the claw is actually a little bit nicer, just because it's like every transposition acts kind of the same.
Right. Yeah. The claw is send everything through 4 or whatever.
So I suppose one of the other things is that if you're claw free and also a tree, then you're the path.
Correct. That's
so
true.
That'll be tough for a number of reasons.
The path is somewhat well understood. I've been given to believe that people understand Bruja order.
The path is also, the geometry is also really, really well fleshed out.
Yeah.
Permutahedral variety style. Very, yeah.
Okay.
I have not thought about trying to work with claw-free graphs and whether or not that would.
I don't know what your first example of a graph that is claw-free and 2-2 avoiding and is not an incomparability graph of a post set. Like, I don't know how big of a class of graphs that is.
So one thing I perhaps should have for those of us who aren't as familiar with the claw-free or the incomparability graph story, what I'm saying is, right, on the Hessenberg side of things, if we have this situation, we also need that. Like visually, like you'd want to put things in an order, and if you skip, then you need everything in the middle.
I guess C5 is the smallest claw-free, 2-2 free graph that's also not the incomparability graph of a post set.
Yeah. The other issue that really comes up quite a bit is that after the four claw is the only up to isomorphism is the only example that isn't in that class. And if you bump yourself up to 5, then you have to do computations in S5, and the layers of definition make it difficult to code. I've made some progress with that. Yeah.
That's believable. Well, thank you. Does anyone else have any questions? Okay, then I think we can thank our speaker again.